You know, people are always asking me, can we reverse aging? Can we go backwards in time? Can we make things young again? And I have to tell you, the answer is built right into the fabric of nature itself. It's not a matter of technology or waiting for some future breakthrough. It's about something much deeper, something that sits at the very heart of how the universe works. And that something is the second law of thermodynamics. Now let me tell you what this law says, and then we'll dig into why it means what it means. The second law says that in any closed system, entropy always increases. Always. Never decreases. And you might say, well, what's entropy? That's a good question. Entropy is a measure of disorder. Or if you want to be more precise, it's a measure of the number of ways you can arrange things microscopically while still having them look the same macroscopically. The more ways you can arrange things, the higher the entropy. Let me give you an example. Suppose you have a room, and in one corner of the room you have all the air molecules bunched up together. That's a very special arrangement. There's only a few ways to have all the molecules in that corner. Now, if you let those molecules go, they spread out all over the room. Why? Because there are enormously more ways to arrange those molecules when they're spread out than when they're all bunched together. The molecules aren't trying to spread out. They're not thinking, oh, I should go over there. No, they're just bouncing around randomly. And statistically, they end up exploring all the configurations available to them. And since there are so many more configurations where they're spread out, that's where they end up. That's entropy increasing. Now, here's the thing. You never ever see the reverse happen spontaneously. You never walk into a room and find all the air molecules have accidentally bunched up in one corner. Why not? It's not impossible. The laws of motion for each individual molecule are completely reversible. If you filmed a single molecule bouncing around and played the film backwards, you couldn't tell the difference. The laws of physics at the microscopic level don't care about the direction of time. They work just as well forwards as backwards. But when you have a huge number of molecules, something remarkable happens. The statistics take over. Yes, it's possible for all the air molecules to bunch up in one corner, but the probability is so stupendously small that you could wait longer than the age of the universe and never see it happen. This is what we mean when we say entropy increases. It's not a law about individual particles. It's a law about statistics, about probabilities, about what happens when you have enormous numbers of things interacting. And this is where time comes in. You see, the second law of thermodynamics is the only fundamental law of physics that distinguishes between past and future. All the other laws work the same if you run time backwards. Newton's laws, Maxwell's equations, even quantum mechanics at its core, they're all time symmetric. But the second law isn't. It says things go one way, from low entropy to high entropy, from order to disorder, from concentrated to spread out. And that direction defines what we call the arrow of time. When you crack an egg, the egg doesn't spontaneously uncrack itself. When you stir cream into coffee, the cream doesn't unstir itself back out. When a glass falls and shatters, the pieces don't leap back together and form a whole glass again. Why not? Because all of these processes involve a massive increase in entropy. The broken glass has many, many more possible arrangements of its pieces than the whole glass does. The stirred coffee has many more ways to arrange its molecules than the separated coffee and cream, and once you've gone to that high entropy state, the probability of randomly going back to the low entropy state is essentially zero. Now let's talk about aging. What is aging really? It's a process of accumulation. When you're young, your cells are well organized. Your DNA is mostly intact. Your proteins fold correctly. Your mitochondria generate energy efficiently. Everything is in a relatively low entropy state, at least as far as biological organization goes. But as time passes, errors accumulate. DNA gets damaged. Proteins misfold. Cellular machinery breaks down. Free radicals cause oxidative damage. Telomeres shorten. All of these are irreversible processes in the thermodynamic sense. Now you might say, wait a minute, we can repair some of these things. We can fix damaged DNA. We can replace broken proteins. Yes, that's true. But here's the catch. To repair something, to reduce its entropy locally, you have to increase entropy somewhere else. Your body uses energy to perform these repairs, and that energy comes from breaking down food molecules. When you break down food, you increase the entropy of the universe. You take ordered molecules like glucose and you turn them into carbon dioxide and water, which are much more disordered. The entropy you decrease in your cells by repairing them is always less than the entropy you increase in the environment by consuming energy. This is crucial. You can fight entropy locally, but only at the cost of increasing it globally. Life itself is a process of maintaining local order by increasing disorder elsewhere. That's what we do. We eat food, we break it down, we use the energy to keep ourselves organized. But the total entropy of the universe goes up, and as we get older, the repair mechanisms themselves start to fail. The machinery that fixes the damage gets damaged, and once that happens, the accumulation of entropy accelerates. Now, people talk about reversing aging, and what they usually mean is repairing all this accumulated damage. They want to fix the DNA, replace the broken proteins, rejuvenate the cells, and in principle, you could do some of that, but you can never reverse it completely, and here's why. To reverse aging completely, you would need to take a high entropy state, an old body with all its accumulated damage and disorder, and transform it back into a low entropy state, a young body. But the second law says you can't do that without increasing entropy somewhere else by even more. Let's think about what this would really mean. To reverse aging, you would need to know exactly how to undo every single change that has occurred in the body over decades. You would need to know which DNA base pairs got damaged and restore them to their original state. You would need to know which proteins misfolded and fold them back correctly. You would need to know which cells accumulated waste products and remove those wastes. You would need to restore the exact configuration of molecules that existed when the body was young. But here's the problem. To do that, you would need an incredible amount of information. You would need to know the exact state of every molecule, or at least every biologically relevant molecule in the body. And even if you had that information, even if you knew exactly what needed to be fixed, the energy required to perform those repairs would be enormous. And remember, every joule of energy you use increases entropy somewhere. Now there's another problem, and this one is even more fundamental. As we age, we don't just accumulate damage, we also lose information. When a cell dies, the information contained in that cell is gone. When DNA is damaged beyond repair, the original sequence is lost. This information loss is irreversible. You can't get it back because it's been converted into heat, into random motion of molecules, into entropy. It's spread out into the environment, and it's gone forever. This is like trying to unscramble an egg. Once you've scrambled it, the information about where each molecule of white and yolk originally was has been lost. It's been converted into the random motion of mixing. You could try to separate the white from the yolk, but you can never get back the exact original configuration because that information is gone. It's been erased by the increase in entropy. And here's where it gets really interesting from a physics perspective. The second law of thermodynamics is deeply connected to the arrow of time. The reason we remember the past but not the future is because of entropy. Memory requires creating a physical record, and creating a record means arranging matter in a specific low entropy configuration. We can create records of the past because the past was a lower entropy state. We can't create records of the future because we haven't gotten there yet. Our brains work by creating memories as we go forward in time, and that direction is defined by increasing entropy. If you could somehow reverse entropy, if you could make things go from high entropy to low entropy, you would reverse the arrow of time itself. But you can't do that, not without violating the second law. And the second law isn't just a law we've made up. It's been tested over and over again in every physical system we've ever studied, and it always holds. Always. Now let me address something that people often bring up. They say, what about Maxwell's demon? This was a thought experiment proposed by James Clerk Maxwell, the same Maxwell who gave us Maxwell's equations for electromagnetism. Maxwell imagined a tiny demon who sits at a door between two chambers of gas. The demon watches the molecules, and whenever a fast-moving molecule approaches from the left, he opens the door and lets it through to the right. Whenever a slow-moving molecule approaches from the right, he opens the door and lets it through to the left. After a while, all the fast molecules are on the right and all the slow molecules are on the left. The right side gets hot and the left side gets cold, without any work being done. The entropy has decreased, violating the second law. But here's the catch, and this is beautiful. The demon needs to measure which molecules are fast and which are slow. To do that, he needs to store information about the molecules, and when his memory gets full, he needs to erase it to make room for new measurements. And it turns out, as was shown by people like Leo Szilard and later Rolf Landauer and Charles Bennett, that erasing information generates entropy. The entropy generated by erasing the demon's memory is always at least as much as the entropy decrease caused by sorting the molecules. So the second law is saved. You can't beat it, not even with a clever demon. This is relevant to aging because any process of reversing aging would require something like Maxwell's demon. You would need a mechanism that could selectively repair damage, that could sort out the good molecules from the bad ones, that could restore order. And that mechanism would need to process information, and processing information has an entropic cost. The more precisely you try to reverse the aging process, the more information you need to process, and the more entropy you generate. Now, I'm not saying we can't slow down aging. We can. We can eat healthy food, we can exercise, we can avoid toxins, we can repair some kinds of damage. All of these things can slow the rate at which entropy accumulates in our bodies, but we can't reverse it, we can't go backwards. We can't make an old body young again in the thermodynamic sense. There's another aspect to this that I find fascinating, and it has to do with quantum mechanics. In quantum mechanics, we have something called unitarity, which says that information is never lost. If you know the quantum state of a system at one time, you can in principle calculate what it was at any earlier time. The evolution of quantum states is completely reversible, so at the quantum level there's no arrow of time, no preferred direction. But when you have a macroscopic system with many particles, something interesting happens. The system becomes entangled with its environment. Information that was once localized in the system spreads out into the environment. This is called decoherence, and it's what makes quantum systems behave classically. The information isn't destroyed, it's still there in principle, but it's become so spread out and so mixed up with the environment that it's practically irretrievable. This is another manifestation of increasing entropy. The information has gone from a localized, low entropy state to a delocalized, high entropy state. And this is exactly what happens with aging. The information that defines a young body, the specific arrangement of molecules and cells, becomes increasingly scrambled and mixed up with the environment as time goes on. Some of it is lost to heat, some of it is lost to waste products that are excreted. Some of it is lost to cells that die. The information diffuses away, and once it's diffused, you can't get it back. People sometimes ask me, but what if we had infinite energy? What if we didn't care about the energetic cost of reversing aging? Would it be possible then? And the answer is still no, because it's not just about energy, it's about information. Even with infinite energy, you still need to know exactly what to fix and how to fix it. And that information has been lost. It's been erased by the irreversible processes of thermodynamics. Let me give you another analogy. Suppose you have a movie of a glass breaking. If you run the movie backwards, you see the pieces flying together and forming a whole glass. It looks weird because we know that doesn't happen in real life. But why doesn't it happen? Every individual collision between molecules, every crack that forms, all of these microscopic events are in principle reversible. If you could reverse the motion of every single molecule, you could make the glass unbreak. But to do that, you would need to know the exact position and velocity of every molecule at the moment after the glass broke. That's an enormous amount of information. And where would you get that information? You can't get it from the broken glass itself because the breaking process erased it. The information about the exact state of the glass before it broke has been converted into heat and sound and the random motion of pieces. It's gone. Aging is like the breaking glass. Each moment that passes, each biological process that occurs, each chemical reaction that takes place, it all erases a little bit more of the information about the earlier state. And once that information is gone, you can't reverse the process, no matter how much energy you have. Now there's one more thing I want to talk about, and that's the connection between thermodynamics and cosmology. The reason entropy can increase in the first place is because the universe started in a very low entropy state. Right after the Big Bang, the universe was extremely uniform, extremely smooth, and you might think, well, uniformity sounds like high entropy, but actually for a gravitating system, uniformity is low entropy. High entropy for gravity means clumping, it means structure, it means stars and galaxies and black holes. As the universe expands and evolves, gravity causes matter to clump together. This increases entropy. Stars form, they burn, they create heavy elements, they explode, black holes form and grow. All of this is entropy increasing. And eventually, in the far future, the universe will reach a state of maximum entropy, what's called heat death. Everything will be at the same temperature. All the stars will have burned out. All the black holes will have evaporated through Hawking radiation. And nothing interesting will ever happen again because there will be no entropy gradients left to drive any processes. We live in a universe that is still far from equilibrium. The sun is hot and space is cold, and that temperature difference allows life to exist. Life feeds on this entropy gradient. We absorb low entropy energy from the sun in the form of photons. We use it to organize ourselves, and we radiate high entropy heat back into space. As long as that gradient exists, life can persist, but the gradient is slowly diminishing. The universe is running down. Entropy is increasing. And in the end, billions of years from now, the arrow of time will reach its limit. This is the deep reason why you cannot reverse aging. It's not a limitation of our technology. It's not something we'll overcome with better medicine or more advanced biology. It's a fundamental consequence of the way the universe works. The arrow of time points in one direction, from past to future, from order to disorder, from low entropy to high entropy. Aging is what it feels like to travel along that arrow, and you can't reverse the arrow without reversing the entire structure of thermodynamics itself. Now, I want to be clear about something. I'm not saying we should give up on trying to extend life or improve health. Understanding the thermodynamic limits doesn't mean we can't make progress within those limits. We can develop better treatments for disease. We can find ways to repair more kinds of cellular damage. We can slow the aging process. But we need to be honest about what's possible and what isn't. True reversal of aging, going backwards in time thermodynamically, that's not in the cards. It's forbidden by the laws of nature. And maybe that's okay. Maybe the fact that we age, that we change, that we eventually die is part of what gives life meaning. If we could live forever, if nothing ever changed, would that really be better? I don't know, but I do know that the physics tells us we can't. The second law of thermodynamics is the most fundamental law about the direction of time, and it says we can only go forward, we can only age, we can only increase in entropy. That's the nature of time itself. So when someone asks me, can we reverse aging, I tell them, no, we can't. Not because we're not smart enough or we don't have the right technology, but because the universe doesn't work that way. The arrow of time only points in one direction. Entropy only increases, and aging is simply what it means to exist in a universe governed by the second law of thermodynamics. That's the answer. That's why you cannot reverse aging.